So please sit down. So today we have the pleasure and the honor to have with us Professor Vassilis Angelopoulos. Let me say 2 words before we start. Professor Angelopoulos is an internationally renowned scientist in the fields of magnetosphere physics and in general space plasma physics. He has been the principal investigator of Themis, the scientific and technical lead of the NASA MIDEX Explorers MIDEX mission since its inception in 2001. He is currently working on storms and substorms at Earth while incorporating new data from the Moon's plasma environment as part of the Artemis mission. He also is the head of the Electron Loss and Fields Investigation CubeSat ELFIN, funded by NASA and NSF, launched in 2018. A pair of tiny satellites to study how electrons are scattered from the radiation belts from the electromagnetic waves, a process which powers the aurora. Professor Angelopoulos worked at the Applied Physics Laboratory from 1993 to 1995 and then joined the University of California in 1995. Now he's a professor of space physics in the Department of Earth, Planetary and Space Sciences at the Institute of Geophysics and Planetary Physics at UCLA. He received his American Geophysical Union's James Magellan Medal in 1993 and the Zeltovich Medal by the Russian Academy of Science and COSPAR in 2001. So, please, you can take the floor.
Thank you very much.
It will be in English because
I'm so glad you said that. It's so hard to say. Yeah. Stroboplasmatos and everything else in Greek.
Yes.
How is the living meeting approach? Υπήρχε τα υπόλοιπα να δουλέψουμε. Είχε στο... Yeah. Να τα φέρουμε λίγο πιο πάνω. Οκ. Έξι στο meeting. Μ' ακούτε καλά? Ωραία. Thank you very much for the invitation. I'm so pleased to be here and see all of you, and I'm very honored by the opportunity to talk with the Academy here. And I want to give you an overview of where I think we are and where I think we are going with the magnetospheric, in particular magnetotail physics. I'll give you a perspective over the last 20 years, where the field has been and where the field is going in the future. And I'll also mention a few upcoming missions that are designed to address the big problems in the field right now. And energy partitioning in the aftermath of tail reconnection bridges the gap of where we were. That is what causes energy releases in the magnetosphere, which is tail reconnection, to where we're going, is how is this energy that is released during reconnection, how is this energy converted to heat in the magnetosphere and the near-Earth environment, causing space weather. So, the Earth is buffeted by the solar wind that emitted occasionally abruptly in large bursts, related to energy at the base of the solar corona, principally magnetic energy that there too is converted to kinetic energy by magnetic reconnection. But large coronal mass ejections are occasionally emitted, creating powerful auroras and energizing charged particles in the Earth's environment, causing space weather. How exactly this happens is unclear. This is the point of the discussion today. But I really want to mention that the phenomena that we study here at Earth have also occurred in other astrophysical plasmas, like in this case on so-called Herbig Haro objects, which are young stars that are still accreting, and the accretion process going closer to the star is facilitated by shedding angular momentum that is contained in these circulating plasmas, shedding that from the poles by emitting these jets from the poles of the star, liberating this angular momentum and enabling accretion to proceed. So this would not happen without, arguably, magnetic reconnection happening at the base of the accretion, according to several models. So again, plasmas are related here to the evolution of young stellar objects. They're also related to the evolution of planetary formation, like 5–10 million years after a star's internal fusion energy starts being liberated, extremely high-speed stellar winds are emitted, and they stop the accretion and allow the planetesimals to start interacting only gravitationally, forming gradually the protoplanets. And again, these are called T-Tauri winds because they're observed in T-Tauri stars first. They were observed first there. And they're extremely high-speed solar winds, stellar winds. Again, implicated in the formation of planets. But looking at it from a very far perspective, stellar interaction with interstellar medium also is, you can host interactions, plasma interactions, like the ones we observe in the magnetosphere. And here you see two images of the mirror and of betelgeuse that depict the interaction of supersonic winds from the planet, from the star, interacting with interstellar medium, forming shocks, termination shock, and the shock ahead of the star moving through its interstellar medium. So objects like that abound in the universe, but here at Earth, we can study them with great detail, with our sort of eyes and ears, with our sensors out there, measuring the plasma interactions in situ, and relying with any imaging that we can get to provide context. So this is the topic of our discussion today. How is the energy liberated inside the magnetosphere to cause violent energy releases? The interaction in the Earth's magnetosphere with the solar wind, unlike the outer planets, is through electromagnetic interaction with the wind, meaning that the wind's magnetic field, when it is anti-parallel to the Earth's magnetic field, pointing north, when the planetary field is pointing south, there is a possibility for reconnection, and this is what happens there. And reconnection is actually a spigot. It's not where the energy is released, but it actually causes the magnetic field lines to change their connectivity. Rather than connecting to the sun, at least on one side, they're connecting with the Earth on one side. And this creates Maxwell tension, Maxwell forces, that then, as the wind is passing by the Earth, it is pulling the other field, the other leg of the field line, past from the day side to the night side above the auroral ionosphere. It's pulling it back. And as the wind is moving faster and faster behind the Earth, you can see the kink in the magnetic field here that creates a current. There is an electric field due to the motion. The J dot T is such that the electromagnetic energy, magnetic energy, is then converted into, kinetic energy is converted into magnetic energy in the interior of the magnetosphere. There is a pointing flux vector there. So that causes magnetic energy to be loaded inside the magnetosphere. And another process of reconnection at the night side, as seen here to the right, is liberating that magnetic energy into kinetic energy. That comes from the tension of the magnetic field in the aftermath of reconnection. And that tension accelerates the plasma, causing the conversion of the magnetic energy to plasma energy, kinetic energy, and thermal energy. So you can imagine that the magnetic energy in this volume is reduced, and it is transformed into plasma energy. So this is the basic concept that was postulated in the early 60s, that is the dominant energy conversion process in the magnetosphere. The details are things that we're trying to study since then. This dynamic process causes a very dynamic plasma environment around the Earth that you see here depicted as plasma sheet, magnetotail lobes that are embedded with strong magnetic fields. Plasma sheet has high beta plasma, that is more plasma energy comparable to the magnetic energy. In the near-Earth environment, you have outflows from the ionosphere that cause high-density plasmas that correlate with the Earth. That is the plasma sphere. And field line currents connect these regions, so transfer forces from one region to the other. So you have an imbalance of forces that causes field line current, and that causes the force to be transmitted to the ionosphere to push ionospheric plasma around. So you can see how this medium is very interconnected and very dynamic. The ionosphere is at the mercy of what comes from the magnetosphere above as electric fields and as field line currents. It is set into motion in the same sense as the entire magnetosphere is set into motion. And those currents cause strong dissipation and heating in the ionosphere and cause plasma irregularities that then may cause scintillation of GPS signals and space weather phenomena of a different kind in the ionosphere. They have to do with UHF transmission that is disabled by the presence of scintillations that are comparable to the wavelength of those waves. So you've got space weather phenomena out of the magnetosphere related to the particle energization with very high energies that penetrate the skin of satellites and humans. And in the ionosphere, you've got phenomena like scintillation, ionospheric scintillation causing loss of electromagnetic signals, also heating of the ionosphere causing increased drag of the satellites, and many other phenomena like that. So there is a reason why people are very interested in modeling and predicting this phenomena that was top of mind since the Cold War and ever since with the increased reliance on space technologies. And so back then in the mid-70s and early 80s, the so-called Open project was proposed. It turned into the ISTP project that was a collaboration across many international players, NASA, the Russian Space Agency, JAXA, ESA, and many others. And they agreed to put together fleets of satellites, coordinated, that monitor different parts of the system, the solar wind, the wind mission, the polar ionosphere, the polar mission, the magnetotail, the geotail, Japanese mission, Interball was a Russian mission, and so on. And there was like a handful of, missions that were very expensive back then, to the tune of 55 billion. In the end, international collaboration did not work exactly as planned, but the synergy between these missions gave us a picture of how the system works. And we realized that this energy circulation through the magnetosphere is not steady, it's quite unsteady. And it occurs in fits and spurts, which we call substorms and storms. The substorms are fairly minor activation, quite repeatable. We have a few of them every day, last for a few hours. And they are best envisioned if you look at the aurora from top down. This is a movie from the image mission that shows you what happens. So if I can click on this. This 6-hour sequence of the aurora looked at from the top in UV, so you cannot really see the day side, but the sun is to the left. But you cannot see the day-night difference because of the UV light. But that is not affected by the daylight. So we can see is the aurora here. And you can see that this aurora brightens abruptly in a period of the order of half an hour, and then expands forward, and then let me see if I can, how can I make this play? Got the symbol here. Worked before. There we go. So you can see an eruption happens here, forward motion, another eruption here, forward motion. This is, they lasted 3 hours or so in this 6-hour sequence. They're highly repetitive. And so this is something we could potentially study if we actually tune our spacecraft to it. And that's what we did actually. But it's highly complex. And the reason you can see in this simulation of the equatorial magnetosphere on the night side. And so this is a plane that is coming out of the page in this picture. And it's shown here, in XY plane. X points towards the sun, Y is towards dusk. And so what is imaged here is the density and the flows. And you can see over the period of several hours, these flows are highly episodic. And you can imagine they come in. And presumably from tail reconnection, actually we know it's tail reconnection in this image, this simulation. They come in and they bring energy towards the inner magnetosphere. You can imagine how the aurora lighting up every time this happens. So very dynamic. And so how do you prove this is true? This is a model. How do you line up satellites to prove? And the most difficult question to address back then, in the early 90s, was, well, where do these things start? Do they start close to Earth, where the energy release is most intense because the current is most intense there, and the electric fields are strong? Or does it actually start at the putative reconnection location out here, 20 to 30 ARI? And there was a big dichotomy in the field. We don't know where subsystems start, what makes them, what triggers them. And this is the topic of the Themis mission that was launched to determine where this occurs first, so we can put, we can focus our attention to the instability that causes the substorms. The other big mode of convection or circulation is storms, magnetic storms. These are much bigger than substorms. They occur where the solar wind driver is very strong. They last for many days, and they have a clear main phase where a lot of strong electric fields are observed, and the recovery phase where the electric fields are a little weaker, but still the energization of the inner magnetosphere is retained over a long time. And that is the time when electrons are actually accelerated to very, very high energies. Most satellites are zapped 2 or 3 days after the storm main phase. So how do they get powered? What power storms? That was a much more difficult question to address. And only now are we beginning to address the inner workings of storms after the knowledge we have acquired from how substorms.
Can I ask you a question?
Yeah.
You're showing this picture of the reconnection, and in a movie that you showed previously, you showed that happening continuously.
Right.
As if you're accumulating flux on Earth.
Yes.
You cannot do that forever. How does that operate? Does it stop at some time and starts again?
Well, on average, the question is how does the circulation occur? Is it continuous or discontinuous? And how do we address this observationally? And what we have found out, it is not continuous. It is quite abrupt. And on average, the amount of flux that we obtain from the day side reconnection to the night side must equal the flux that we bring to the Earth, so that the circulation on average does not deplete the flux. The flux is conserved. But this does not happen in a continuous fashion. It happens discontinuously in fits and spurts. And this is what the movie actually depicts, that it is extremely dynamic. So I don't know if this answers your question.
So the magnetosphere closes and opens again?
In part, yeah. In part, you have
a part where it opens with no reconnection. On the night side,
well, what happens is that an amount of flux is depleted from the day side, and an equal amount of flux will have to be reconnected to the night side to make up for it, so that when these flux bundles have been reconnected, they will eventually make it to the day side. So the circulation is built up by flux bundles that reconnect sporadically. So on average, the flux remains conserved.
So the reconnection on average happens continuously.
On average, continuously, yeah. And that's all dictated by the amount of.
There is a circulation.
There is an average circulation that's dictated by the average electric field of the solar wind. Yeah. But the question is how? And so one of the interesting things and most puzzling things back in the early 80s was that if you take a flux bundle from the night side and let it convect towards the near-Earth region, that will compress the plasma inside of it. And the compression of the plasma, assuming PV to the 5/3 is constant, which means that there's adiabatic evolution, is inconsistent with the evidence that what is the magnetic field is a function of distance. The magnetic field as a function of distance on average looks like this. There's the black lines here at the bottom. But if you take the flux bundle and move it according to PV to the gamma earthward, the compression of the flux tube will be such that it will deplete the magnetic field so that the field line, effective field line length, will be different from the model. So our average statistical models of the magnetic field are inconsistent with steady state adiabatic convection from the night side inwards. And that is a puzzle. How does the plasma convect if the convection does not match expectation of the magnetic field and pressure balance with the load? And the reason why these are inconsistent is because when you load the magnetic field lines here with some density, one way to get out of this problem is you can lower the density of the plasma here to be much less than the surroundings. So that if, say, reconnection caused this flux tube to move earthward, then the density would be consistent with low density near zero. And when you would bring that flux tube inward, then you would be able to come in without violating the average magnetic field observed. So these two lines, the dashed and the black lines, will be similar to each other. Observations, the solid lines, would match the modeling, which is the dashed line. That's what Pontius and Wolf suggested, is that those flux tubes are loaded with low density plasma. And when the way they explained it as if the density of the flux tubes is lower than their surroundings, these fluxes would interchange with their surroundings, able to come in closer to the Earth. There are many ways that you can understand that. One way to understand it is to see that the diamagnetic current that passes through, which is a grad P cross B drift across, is nominally dustward, but in the flux tube is a smaller current than in the medium outside. So there is a field line current that is built up on the two sides, connects to the ionosphere, creates an electric field, pushes the flux bundle earthward. That's one way of explaining the motion of the flux tubes. They were postulated in order to get around this pressure balance equidistance I mentioned earlier, and they were first observed. They were modeled with MHD models as shown here on the right, and they were observed based on my thesis work back in the early 90s. They were observed to exist. This is a percentage of high-speed flows in the plasma sheet as a function of activity index in the horizontal line. More and more of them observed for high activity. So high-speed flows exist. They're similar to what were postulated by Pontius and Wolf because they come with low density and high magnetic field. And they are actually responsible for a large fraction, almost 100%, of the earthward transport of energy density and of magnetic flux. So they are the pieces that constitute convection in the plasma sheet. and they are consistent with the Pontis-Wolff model of underdense flux tubes originating somewhere in the midtail, being able to convect closer to the Earth. As they do so, studies have shown that in the aftermath of reconnection, in fact, they are responsible for most of the energy conversion that is attributed mostly to enthalpy, ion enthalpy, which is in normalized units to some speed, the Alfvén speed, and some nominal quantities in the plasma sheet. The enthalpy is higher than the Poynting flux, which is higher than the electron enthalpy. And so most of the energy in during the high-speed flows, in the aftermath of reconnection in particular, is converted into kinetic energy and thermal energy of the ions. So we know then that heating occurs in the aftermath of or during the high-speed flows, and they're responsible for energy conversion. But the big question remained, as I mentioned earlier, where do these things start? And so in the past 20 years, the Themis mission focused on what triggers the substorms that cause the avalanche of energy in the magnetosphere. And there is evidence that I mentioned earlier from the day side that reconnection is not really where the energy occurs. For example, the day side reconnection, in the case of day side reconnection occurs here at the day side magnetopoles. But energy conversion occurs up there, where J dot E is less than 0, and therefore the kinetic energy is transformed to magnetic energy in the high latitude magnetopoles on the night side. And similarly, in the case of night side reconnection can happen here at 20 to 30 RE, but energy conversion can happen in the aftermath closer to the Earth. And again, reconnection is a spigot releasing or enabling the release of magnetic energy into thermal energy. So it was unclear back in the 90s where things start. And Themis put his spacecraft out here to try to determine where things start first, and then focus our attention to the right things. And what is the cause and the effect, and set our minds correctly when we study these problems. So I'll discuss this first, and I will then move on to what is the question of the future. And the question that we want to address from now on is how does the magnetic energy from the reconnection gets converted into heat when the flux bundles, the connected flux bundles, approach the Earth. And here, where is the most dynamic region, the highest energy conversion occurs close to the Earth, how does this happen? And I'll tell you from now that the reason why we cannot resolve this problem now is because we don't have spacecraft in tetrahedral formation that allow us to study vector quantities like the current, pressure gradient, and so on. We never had that before. And what we need to do is have such tetrahedral formations in the near Earth plasma sheet to address questions of energy conversion there. And I'll talk to you about some missions that strive to do that.
Can I ask another question?
Yeah.
In this picture, this orange region is plasma or just magnetic field for you? Does plasma come from the sun? Does the Earth environment have plasma?
Yes, 50-50. 50% of the plasma
comes or the Earth?
So 50% comes from the Earth, 50% from the sun on average.
The atmosphere of the Earth.
That's right. It has polar winds coming up and polar outflows, and also ionospheric heating from the bombardment of energetic electrons causes the electrons to come up. Ambipolar electric fields cause the ions to come up. And so 50-50, and it varies with activity. So in fact, we can track that from singly or doubly charged helium. The doubly charged helium alphas come from the solar wind, singly charged helium from the ionosphere, and you can take the ratio and find out what percentage comes from the ionosphere. So on average, 50-50. All right, so what did Themis do address the question where things start is it placed 5 satellites so that they line up on resonant orbits. Once every 4 days, they line up along the Sun-Earth line and track the flows that come from reconnection and time things so we can determine whether reconnection starts first out here or whether the ionospheric eruption starts first or the near-Earth plasma sheet energization starts first, and where do things start first. We know the time scale of propagation, Alphen time scale, is order of tens of seconds. And so we needed faster time resolution of tremors. Our resolution is 4 seconds. And with this kind of time cadence, we're able to determine that during substorms, in particular during the onset of substorms, tail reconnection starts first. It is followed by brightening of the aurora. And finally, it is followed by energization of the near-Earth environment, presumably as the flows come in and they hit the plasma in the near-Earth environment. So with that behind us, when we're able to make strides into the physics behind this acceleration of and heating of plasma in the aftermath of the reconnection outflows. So this is a picture that depicts the meridional plane, and this is the equatorial plane of flux bundles coming in the aftermath of reconnection, and measurements by the 5 Fermi satellites of the magnetic field and of the flows. I'm not sure if the flows are shown here. Maybe these are the flows. I'm sorry. So these are the flow vectors. And the shaded region depicts the magnetic field orientation. So they were seen to come in one satellite after the other. So you can see the time delays of the magnetic field dipolarization. The field turns in the northward direction at the satellite location, as if there were no current in space. All the current was from the dipole of the magnetic field of the Earth. That's why it's called a dipolarization. So an abrupt increase of the magnetic field in the z direction it's called a dipolarization. The bundles that come in the aftermath of reconnection are called dipolarizing flux bundles, and they accompany these high-speed flows. And actually, they're the reason for the high speed of the flows. The dipolarization of the field causes a very strong curvature force that is accelerating the flow earthward. But in the ionosphere, they're also seen as brightenings of the aurora. And in fact, these are images of the aurora from the ground up, but arranged as if the observer is from space looking down. And up means towards the North Pole, and down means towards the equator. And so the auroral oval is in this region here, in this region over, I have to find the mouse. Okay, over here. And this is the poleward edge of the aurora. This is the equatorward edge of the aurora, where the pre-existing quiet arcs map. And this down here maps to the inner magnetosphere, the radiation belts. So this is the auroral oval. And what you see at the onset of the substorm, just prior to the onset of the substorm, is a poleward arc intensification, a north-south arc coming down. And then when the arc, north-south arc approaches the pre-existing pre-substorm arc, then a brightening happens and the pre-existing arc moves forward and expands. That's the substorm onset. So there's a precursor to the onset associated presumably with tail reconnection far out at 2030 that instigates the north-south arcs. And presumably as the flows come in, that's where the north-south arcs mark. And then as the flows interact with the near-Earth environment, the inner edge of the plasma sheet close to the inner magnetosphere, that's when the auroras erupt. So pretty telling sequence. This is a superposed epoch analysis of things like the magnetic field, BZ, north-south is the red one, and that's the indicative of dipolarization. This is energetic particle fluxes, so very intense, an intensification of the flux happens right there. there is a reduction of the density. This is what I was calling previously the underpopulated flux tubes coming from the tail, being able to convex without problem. And temperature increase in the ions, electrons as well. PV to the gamma, these are the quantities under dense flux tubes, have low entropy and they can propagate closer to the Earth, and the high-speed flows. So you can see in a nutshell, a validation of the Pontius and Wolf hypothesis and how it works in the case of the substorms. Now, I mentioned that the dipolarizing flux bundles are accelerated by curvature force. We can measure that with 3 Fermi satellites here when they are locally situated so that they are predominantly separated in a meridional configuration. So you can determine the curvature of the field. When you do that, then you can measure the curvature force. And you can integrate that and find out what is the acceleration the plasma gets and integrate that to get the flow velocity that results from that acceleration. And you get agreement with the observed flow velocity. And so what happens is that the curvature force accelerates the plasma and hits the plasma ahead of it. The heated plasma pushes back with the pressure gradient force, and the imbalance between the curvature force and the pressure gradient force is the net force associated with the inertia force, rho v dv dt. You can integrate that and get the velocity. So that's how the acceleration happens. You can see that in the pressure profile, as the flow burst approaches, the pressure increases and then decreases behind it. This pressure bump here is the pressure gradient that is pushing against the flow burst coming in and is accelerating the pre-existing plasma around it. So it's kind of churning the plasma around. So this is a dynamic view of the interchange instability that's more an energy principle view. The acceleration of the ambient plasma is seen in data here. These are pressure, statistical analysis of pressure data around the flow burst coming in. And this is modeling of the injected ions interacting with the approaching flow burst just by single particle trajectories. And they have a similar gradient and similar anisotropy towards the dust. On the right is statistics of the currents associated with the flow burst coming in. The flow burst has a magnetic structure that is this red field lines here. And the currents surrounding it are shown here. This is the cross-tail current. It is diverted around and is continuing here towards the dusk. But when you move to higher latitudes, these currents start to become more and more field aligned, like so. Presumably, they connect also to the ionosphere, feed some of that current to the ionosphere. So we can build a statistical picture of how these bundles interact with the ambient plasma. There are sites, these flux bundles. There are sites of ion-electron separation. This is the whole electric field measured at the interface between the bundle and the ambient plasma. And this whole electric field is created by electron-ion separation. Whereas here on the right, you see the high-resolution electric field that's highly variable, and that causes violation of the even of the electron frozen-in conditions. So these sites are also important for electron acceleration, non-adiabatic phenomenon. We were lucky that several years after the Themis launch, we took 2 of the Themis 5 satellites, we took them around the moon and created the so-called Artemis mission. From that vantage point, when Themis satellites close to Earth are correlated, that is, are lined up with the moon, that is in full moon, then we can do conjunctions between flows that are tailward on one side and earthward on the other side to look at energy conversion at the 2 locations simultaneously. So what we can find is that the energy conversion in the tailward flows is far smaller than the energy conversion in the earthward flows because the magnetic fields are weaker here, and the cross-tail currents are also weaker. So J dot E is much smaller. This is shown in this event, this conjunction study, but you can integrate the J dot E that you observe at the satellites, and you can determine how much energy is converted by the flows moving earthward from some putative neutral point, say somewhere at 20 or 30 ARI towards the Earth, by integrating the energy conversion J dot E in the volume of the plasma. And you can find out from the difference is on the order of about 3 petajoules. And this is also the typical energy released during a typical substorm. So the energy conversion is happening along the flux tubes coming in. And as the J dot E is increasing closer to the Earth, is consistent with the energy conversion during the entire substorm. So this happens pictorially as shown here. This is the reconnection flux bundle. It's got the flow velocity, it's got a cross-tail electric field due to its motion. It's got a Jy along it because of the curvature. And J dot E is the one responsible for convecting the magnetic field as the bundle is moving closer to the Earth, leaving a void behind it, carrying a smaller magnetized volume, resulting in a smaller magnetized volume, and therefore depletion of magnetic flux, and the compression of the plasma causes higher pressure here. And J dot E associated with that is the integral of J dot E during the motion. In reality, of course, I'm envisioning the plasma sheet being like so on the top. It's split in two halves, tailward flow on the right, earthward flow on the left. And energy conversion happens at both locations. Weak energy conversion here, strong energy conversion on the left. So it's all related to the Poynting flux equation, where J dot E is linking the energy flow, energy flux in Maxwell's equation, and energy flux in the kinetic gas theory.
But one half of the curvature acceleration will go to the right also.
Correct, yeah.
One half in, one half out.
Yes, well, it is dynamic at about 20 or 30 ARI. The energy conversion is small. As the bundle comes in, there's more and more energy conversion because the magnetic field is stronger closer to the Earth. So the net result is the earthward flow will result in stronger energy conversion because it is responsible for annihilating a stronger magnetic flux.
True, but the origin of this effect is split
in half. Yeah, two pieces. Yeah. These are the observations that are related to what I just said, but I just said it. So P3, which is the inner satellite, has energy conversion and flux transfer that is 10 times stronger or more than the equivalent atom P2, which is on the right side on Artemis, both in terms of flux transfer and in terms of energy conversion. Particle acceleration happens in spades. This is a superposed dipole analysis of energetic ion acceleration on the top, energetic electron acceleration in the second panel of the BZ, the dipolarization of the magnetic field, northward field increasing, flow velocity increasing at the edge of the flow bundle, strong electric field, and strong intensification of the auroral electrojet, bespeaking of active aurora. What happens as a picture from the top down is these bundles are coming in, the accelerated ions and electrons. The ions are drifting to the dusk just because of gravity drift as they approach closer to the Earth. The electrons are drifting to the dawn. And what you see if you're sitting in the dawn, you see an injection of electrons. You're seeing in the dusk an injection of ions, but no electrons. If you're seeing in the middle, you're seeing both. And that's what we see in observations. The point here is that the injection is localized in the y direction, to within 1 to 3 Earth radii. So these are like pencil beams are coming in. Very hard to detect, but of course, with an alignment we had on Themis, we were able to detect them. And simulations of this are shown here, where the electric field associated with the bundle, and the this is the total electric field, this is the inductive electric field, and the flux transfer associated with the bundle.
So the acceleration is happening in the null point of the connection, or
No, that's the point, is that the null point is just enabling the flux magnetic field to liberates the energy. It's enabled the magnetic field to move away from the X point. And as it is moving away, it is also accelerating particles. Therefore, the magnetic flux reduction that's happening for the shrinkage of the flux tube is responsible for the energization of the particles around. But the volume of the X point is so small, and also the magnetic field is so small there, that very little acceleration happens there in the big picture. Yeah, that's why I was talking about reconnection being a spigot for energy release, but not where the energy release happens. Yeah. So, in fact, it's not non-adiabatic acceleration is a big part of this acceleration. This is just images of the equatorial plane in a simulation, MHD simulation, and then Schur-Abdal and al. Took the fields from that simulation and ran particle trajectories through. And they found that the ions are accelerated non-adiabatically in these fields. Of course, they used particle simulations. The MHD is always adiabatic, but the particle simulations can be non-adiabatic. And they found that multiple interactions of an ion with the incoming electric field can result in non-adiabatic acceleration of the ions. While the electrons, when they are accelerated particle simulations for electrons on the right, in a MHD simulation, when the electron trajectories are accelerated in the simulation fields, they give you non-realistic distribution functions that are highly anisotropic. And of course, waves will then relax this anisotropy, but those are not accounted for in the simulations. More studies of this. This is an interaction of the gyrating ions in the process of as the flux bundles come in. This depicts the flux bundle. And because the scale size of the bundle is comparable with the ion gyre radius, the ions have the opportunity of interacting with it, the flux bundle, multiple times, increasing their energy from 10 kilovolts to 60 kilovolts in this case. You can study this statistically and look at the spectrum of the ions, how it develops high energy tails in the process of the interaction with the flux bundle coming in. Artemiev et al. 2015. Similar thing for the electrons. This is the spectrum of the electrons, low and high energy. You can see the spectra showing accelerating electrons in the presence of turbulent electric fields. And this paper by Ergen et al. They model the spectrum of the electrons subject to those electric fields, and they find agreement with the observations, and there's a simple model of this acceleration of electrons in the turbulent electric fields. And you can imagine the turbulent electric fields to be electrostatic fields, electrostatic turbulence, and the electrons gyrating in them. The scale size of the order of the bilength. And as a result, the electrons of a given energy and above have a large enough gyre radius to scatter in this turbulence and get accelerated by it. So non-adiabatic fields, waves are also seen. And in fact, the temperature anisotropy versus plasma electron beta, shown here, shows that the anisotropy can never exceed a certain value that is dictated by the onset of the firehose or the Whistler instability. Means that those instabilities take over and relax the anisotropy, isotropized again, so that the limit is never exceeded. So you've got plenty of waves there, and indeed those waves are observed in these magnetic field spectra, pointing flux spectra to radiate the flux away. And that's all I want to say here is that you see the pointing flux moving the energy away from the anisotropic electrons. In the ionosphere, we observe these things. Imic waves are seen, magnetic ionocyclone waves are excited by the anisotomy of the ions, but are drifting to the dusk, and they actually scatter electrons to the ionosphere. And that electron scattering is causing energetic electron scattering is causing precipitation, but they also scatter ions. These ions are 5 to 10 kilovolt ions that come to the ionosphere and create proton aurora. This is the this region here is called the proton aurora. It's very diffuse at the low latitudes. On the right, you have Whistler mode waves that are seen in this magnetic spectra. These are chorus waves, called chorus waves. They're chirps like chorus, and they scatter low energy, intermediate energy electrons, of course, pulsating aurora. So you can see the pulsating aurora on the ground. So a combination of ground and space observations can really give us the synoptic view of the particle acceleration and energy depletion, and the in situ view from space. More instabilities and more opportunity to explain things like auroral beads, like you see here in the aurora. We don't have to leave the way. Okay. When this happens is at UCLA, this is forced socialization. Right, so these instabilities then are postulated, but it's very hard to determine how much energy is converted by which instability at any given time. And the reason we don't have a multi-spacecraft observations to give us a volumetric rendering of the contribution of each conversion mechanism to the overall energy conversion process. So this is why we would like to see in the future. We would like to see in the future missions that are able to address this question. These are not phenomena that exist only during substorms. Recently, we have observed that during storms, very near Earth reconnection occurs and may be responsible for triggering or causing the main phase of storms, energy conversion in the main phase of storms. So these are observations from the three innermost, the three Fermi satellites of an X line, and the magnetic topology can be reconstructed as the flows move past the satellites. And you can see here a picture of the X line as the satellites move past it in the frame of the X line itself. So in reality, the X line moves tailward, but here I'm showing you the satellites moving earthward in the frame of the X line. So this is consistent with the magnetic observations.
Είναι φυσιολογικό που δίνουμε τα μέσα μας. Δεν ξέρεις πότε θα σου
είναι μέσα πολύ έντονα τώρα.
Ναι, αλλά κάποια στιγμή δεν θα είναι και εμείς
Let's continue.
Yes.
So what I just said is that we have observed very near reconnection in the case of magnetic storms that give us a hint that very near reconnection may be responsible for powering storms. And the reason why I say that is when reconnection occurs so close to the Earth, the flow bundles that are emanating from it have a direct access to the near-Earth environment, the inner magnetosphere, namely the ring iron, where ions are drifting around, and enclosed drift shells, and the radiation belts. In this case, reconnection happened as close as 8 Earth radii, the first time it has ever been observed. But then statistically, we observed reconnection 7 times in the course of 11 years of the full solar cycle. So it's rare to observe, but it happens. Yes.
Do you have a clear null point, or you have also components of the magnetic field that are perpendicular to the current sheet or parallel to the electric fields? These are components that are important for them.
Yes, parallel electric field existed, and anti-parallel magnetic fields normal to the current sheet also were seen. These are all the hallmarks of reconnection. Also, the Hall electric fields were very strong, 100 millivolts per meter, and impossible to miss, even with short electric field antennas on Themis or MMS. But clear hallmarks of reconnection were seen. And as I said, they're very rare. The reason why they're rare is they're only seen when the satellite is close to the neutral sheet within a few ion inertial lengths. This is about 1,000 kilometers. For a satellite to be close to 1,000 kilometers, it's very rare, even with an equatorial orbit. That's the reason these had not been seen before. And the statistical analysis revealed that they're as rare as a few events in a whole solar cycle seen by an equatorial mission like Themis. In fact, there was a very rare case, recent case, 2025, I think, or 24, something like that, where we saw 3 consecutive very near reconnection sites during one storm, when we were so lucky to have Themis in the pre-midnight sector, where these tend to be most often seen, during the main phase of a storm, which is a very fortuitous event. And 3 events were seen one after the other, when Themis was located within a couple of thousand kilometers of the neutral sheet. So we really caught it at the right time. So this rare event shows that if you're located at the right longitude, at the right distance from the neutral sheet, you can see them quite often. This is the reason, localization is the reason why this had not been seen in the past. So now, what do we do in the future to make progress in this area? Like, what is causing the conversion? What process is causing the energy conversion? For that, we need to have to measure gradients of plasma and magnetic pressure, like not only J dot E, but V dot del P, the grad P, grad B, the curvature. All these are vector quantities that it's impossible to measure with a single satellite. You need multiple satellites. Tetrahedron is optimal because then you can make 3-dimensional vector measurements, grad P, grad B, so that you can measure, say, the field aligned generation, like current generation. That is grad P cross grad B. So there's 2 vectors. When they're not co-aligned, they create field aligned current. We want to measure that. And you cannot do that with 3 satellites like Themis. We need a future mission for that. And the Plasma Observatory, and this is what we would like to see. As this activity happens, as the flow bursts come in and interact with the inner magnetosphere, we want to see it as it happens. What happens is that, in this case, the incoming flows increase the pressure in the inner magnetosphere, and that increased pressure region expands tailward. So we want our satellites to be here and measure this tailward expansion and measure the interaction between the flows and the expanding plasma sheet where the conversion happens. And this is something that Themis could do with only 3 satellites, but in the future would like more satellites for that. And in fact, the Plasma Observatory mission, which is a competitor for ESA's next M-class mission, the decision is going to be made this summer, has 7 satellites. It's got 1 tetrahedron and high spatial separations on the order of 1 to 2 RE, and another tetrahedron nested within the larger one, which is a tetrahedron on ion scales, 100 to a few 100 kilometers. So you can measure this gradient simultaneously in the fluid scale and in the ion kinetic scale. And ion is important because most of the energy turns into ion heating. So that's why it's important to go down to the ion scale. So the Plasma Observatory is an orbit of eccentric orbit 8 by 18 Earth radii. And as the Earth moves around, Of course, this orbit is going to turn around and measure the interaction between incoming flows and the inner magnetosphere from distances of anywhere from 8 ARI all the way out to 18 ARI. That's Plasma Observatory for you. It's a cross-scale mission. Also, the US Heliophysics Decala survey, as its highest priority new solar terrestrial probe mission, it wants to fly 24 satellites in the equatorial plane to study the interaction between the mesoscale flows, the bombers, and the inner magnetosphere here, with nested orbits of something like, I don't know what it is, 8 satellites each, and an imager from the poles, or imaging the aurora and imaging the interaction in energetic neutral atoms. Of course, it's a grand scheme, and of course, it would be nice to start building the elements of that with smaller missions if possible. But this is the proposed grand scheme. Finally, the mission Thea, which is a proposed MIDEX, which is on the heels of Themis, aspires to utilize the Themis bus shown here with upgraded instruments and put them in a similar injection like Themis at the bottom left, Thea at the top left, on a single launch vehicle or launched from a ESPA ring, Sherpa ring, as a secondary satellite, and then go from there to their final orbits. And the idea is to put Themis, in this context, in a highly elliptical orbit with low perigee, so that the tetrahedral formation of Themis, plus 1 spare, 5 satellites, will monitor this interaction all the way from apogee to the inner magnetosphere. So you can see not just the outskirts of interaction, but also the effects of that interaction in the inner magnetosphere. So in that sense, Thea is complementary to PO, different orbit, but together they can study the interaction from different locations and look at the gradients of the energy conversion. And so ideally, you want to fly them together. And together, plus if you have the Chinese imaging mission called SMILE, you can also have the auroral imaging at the same time. So international collaboration can really achieve wonders in the future, and that's my hope of what will happen. So in summary, we've learned the critical role of reconnection in initiating energy conversion in the tail. We've learned to recognize the main drivers of this convection and the main energization processes. We just need to determine what are the dominant conversion processes and make quantitative assessments of what are the dominant processes by having a more volumetric rendering of that process. So PO in Europe is a proposal to address this. Thea in the US as a MIDEX is another way complementary to address this. And the two together can put the first elements of the most important mission according to the Decadal survey links with the benefits of international collaboration. So this is my story. Thank you for your attention.
Thank you very much for a very interesting talk. And it's time for questions.
What is the size of these bundles that you mentioned?
1 to 3 ARI. 1 to 3 ARI. Large, but it's like a few times an ion gyro radius. A few times, yeah. The gradients are comparable or smaller than the gyros. The surface, the gradient at the surface. So that's why they can do kinetic physics. They can break the mu of the ions and impart energy to them to very, very high energies, violating the adiabaticity.
Question, I don't know. The Earth's magnetosphere on the night side, does it close or does it extend?
It extends to hundreds of Earth radii.
Does it close eventually?
Well, no, I think it's open to the solar wind. The good portions of it are open to the solar wind. So you can have solar wind stroll electrons, high energy electrons, come all the way from the tail to one of the two ionospheres, depending on the connection of the solar wind magnetic field.
Eventually the lines open or they.
Yeah, they are open. Some of them are open.
Some are open, but some close.
Some close. Some close.
Can you also have a plasmoid thing release also in the tape? So it has to be open.
Yeah, so when you look at the polar ionosphere, one of the two polar ionospheres has low energy electrons coming directly from the sun. The other does not. This means when the solar wind magnetic field, which is reconnected with the Earth, on one side, it points straight to the sun. On the other, to the distant heliosphere. So the one that points to the sun.
Something may come from those lines, right? Even there, from the distant.
Okay.
You have the aurora, the features. Does the size of these features is related to the morphology of these bundles? So, for example, can we like learn something about the geometry of this structure?
Absolutely. So the north-south arcs that I mentioned, their scale size, when you map them to the tail, is comparable to 1 to 3 RE in the magnetotail, indicating that they're mapping to the flow bursts.
And can we learn also something about the size of the null point? Or
Very difficult because once you reconnect it, that means once you reconnect the closed field lines, that means automatically that point will map to the polar edge of the oval, right? So it's very hard to make any sense of radial extent, for example. So yeah.
Perhaps one quick question. I was always fascinated by this adiabatic versus non-adiabatic acceleration. And one thing that I remember is that, of course, you have in those rapid magnetic field configurations, you have the oxygen, for example, that has a gyro period that's too long to conserve the magnetic moment, whereas protons can do that.
Yes.
And my question is, I really don't know that. Is that okay? So you violate, for example, the first adiabatic invariant, but the question is, what happens to the others? Can we measure that?
To the others?
To the other three for two adiabatic invariants.
Oh, those are broken. Once you break the first, you break the others.
You break the others.
Yes, yeah.
Okay.
But for electrons, you may break the second invariant without breaking the first.
Yeah, that's
possible.
okay.
Yeah.
Okay. Can we check if there are questions from here? Unless maybe there are some questions from people that are online.
Σπέρα, λυπάμαι που...
Raised hands, so if someone wants to ask a question, please go ahead. It's okay, I can hear you, I think.
Okay, this is Stamatis
Professor Krimizis is trying to say something, but we don't hear it.
You can't hear me?
The
speaker is open, yes.
Εγώ σας ακούω μια χαρά.
Now we can hear it. Please.
Είμαι Σταμάτης Κρυμιζής. Βασίλη, welcome.
Thank you.
I'm very sorry I just couldn't be there for a very important reason, but I did see how much terrific progress has happened since I was working with the Earth's magnetosphere and reconnection. I have one question. You briefly mentioned the ring current, and I haven't followed the literature, but has anyone ever explained why it is that the ring current is dominated by oxygen, namely an ionospheric source in terms of energy density? And is that some sort of differential acceleration, or what exactly is the reason?
Yeah, I think the main reason for that is that ion outflows from the ionosphere are a dominant component of the plasma under storm conditions. And so because by virtue of the density fraction being significantly dominated by oxygen, then the energy density also follows that, even if you accelerate everything equally, the oxygen tends to dominate the energy density because of its mass. But there is reason to expect, like what we just heard earlier, preferential acceleration, because non-adiabatic acceleration of oxygen is easier to achieve because of the larger gyro radius, that oxygen get a bigger fraction of that energy because of its non-adiabatic acceleration that's possible. So yeah, and Lynn Kistler has done a lot of work in this area. So I think a lot of observational work validates the importance of oxygen in terms of the energy density at storm times.
Okay, thank you for the answer. I get it.
Great, thank you.
Okay, there are no more questions from what I can see. And we send the speaker again.
Thank you so much.
Thank you very much.
Yes.
Great. Our pleasure. Να σου πω τώρα τι θα γίνει. Αν στείλουμε ένα email τώρα, και λέμε παρακαλώ.
Όχι, πρέπει να στείλουμε ένα email.
Θα σου πω.
Υπάρχει επίγον.
Όχι, θα σου πω. Δεν ειδοποιείται η